And as many of you know, almost every one of those was invented by a statistician, people like Leo Breiman and Jerry Friedman and others, things like random forests. Even deep learning was invented by initially a psychologist and then developed by statisticians and eventually made its way into computer science. Anyway, when I started seeing the data sets that clients brought into H2O, they were often very sparse, but also had hundreds of millions of records. And so the first problem you have in visualization is figuring out how can you even display data of that sort. And here, most of you know these issues, but in visualization itself, many functions that you have to use to display or project or reduce the data in some way are polynomial or exponential, and you simply can't do it for many, many dimensions. There's also the curse of dimensionality that involves any procedure that needs to use, say, Euclidean distances or some type of distance function in high dimensionality. And as you know, that specifically refers to the problem that as n, the number of points, stays constant, and p, the number of dimensions in which those points are embedded, as p increases, the histogram of the distances moves toward a constant. They're still differentiated. It's not like it's impossible to calculate them. But if you're going to use the types of error bounds and that you're involved with smaller dimensionality problems, it simply won't work. And of course, the practical problem, the choke point, you can't send more, I would argue, more than about 500 points over the wire. It's too slow, for one thing. And if you do, and you're doing something like a scatter plot or some other graphics, you're just going to make a big black spot on the screen. That's the real estate problem. The choke point problem is, suppose you're using JSON or some type of transport mechanism, it gets big enough that the user is starting to experience delays in perceiving the visualizations. So if you've worked at all with D3 or some of the client-side renderers, you'll find that it breaks down and dies after maybe about 1,000 points. It doesn't die, but it's going to, depending on your machine, really become impractical. By the way, at H2O, we do use T3 for our rendering, but it's based on what I have designed as a visual server on the server side to reduce the number of points. Now we know the cheesy solutions in 2D, they're very old. You can pixelate if it's a 2D, natively 2D visualization problem you're working with. You can project the points if you're doing things like scatter plots or networks and so on. You can project them down to 2D, but you're going to violate the triangle inequality when you do that. And that means in practice you're going to misrepresent your data when you show that. There are tons of papers and conference papers and things that include the recommendation of, oh, just compute the first two principal components. And there's your solution for a high-dimensional problem. Well, it doesn't work. And some of you might have worked with image maps, so you can compute them on a server. You send over a PNG or some type of bitmap representation, and then regions in there, if you're going to do interactivity, either touch or use a mouse or whatever, you can hit test those regions of the bitmap and be able to brush and link and do the other things we like to do with interactive graphics. I would argue that the most viable solution for the high-dimensional problem is aggregation. I'll show you how I do that. You can project, but if P and then P star, the lower dimension that you're going into, if they're vastly different, again, you're going to run into the representation problem. You're going to violate the triangle inequality in that space. So how do we collapse big data into small data? Well, this algorithm, I'll outline it in more detail, but the picture actually tells the whole story. I'm aggregating, and this is a real data set of baseball players. It's the weirdest scatter plot I ever saw, but it has to do with on-base percents and another measure of their performance, percent on base. And I think it's something like base hits or something like that. Now, if we were to do this in 2D, and of course we don't need to do this in 2D, but if we were, what we're going to do is we're going to make balls. In this case, they're disks. And we're going to cover the points. Now we make sure the center of the disks are on real points. So this is not a cluster analysis. This is not k-means, or people have done that. But the problem with those are that you get centroids, and the centroids may not be where any data are. And second of all, with things like k-means, the dispersion within the clusters is not uniform. So these are balls with fixed radius. So everything inside those balls, and I say balls, I assume all of you know that in 3D they're balls, then they become hyperballs and so on. And the radius of those balls is constant. So what you get is the middle representation. Then you replace all the data points with the actual data points that are at the center of the balls. I call those exemplars. And all the other points in there are called members, borrowing from cluster terminology. And the members are within that R radius distance of that center exemplar, and there may be thousands of those, maybe hundreds of thousands of them. But when you actually do the plot, like a scatter plot, it looks exactly like the plot you get if you plotted all the data and used things like hex binning or other techniques that in 2 dimensions attempt to do the same thing. Now, I want to move on to talk about the problem of anomalies and specifically outliers in data, in what I would say are statistical data, that is data that can be represented by some type of error distribution in a given model. And in this case, I'm just showing you a classic regression fit on 3 Gaussians. So not surprisingly, the fitted plane is horizontal here, is level. We're predicting Z from X and Y. Now, simple problem. And because they're Gaussians, I would expect in our H2O fitting software, which is basically, in this case, ordinary least squares, the simplest model, and our RMSE is 1. That's what I generated from the Gaussians. So what happens if we add 1 outlier? We tilt the plane considerably here, and there's another outlier up there. And the question is, how does something like even gradient boosted trees or random forests do? It does terribly. The outliers are really screwing up the fit in this case. And I would argue that we need to worry in these machine learning models, we need to worry about outliers and find ways to downweight them or eliminate them. And as you probably know, most statisticians would say, don't eliminate them unless you know why they exist, because you may be actually fitting a model to a truncated data set without realizing it. The model will be itself wrong. Well, here's some basic principles. I'm sure you all know, but they're definitions that I've constructed to fit what I'm actually doing with these models. I call an anomaly an observation inconsistent with a set of beliefs, and I'm taking a Bayesian position there. I believe you can actually define a set of prior beliefs about a set of outcomes, and when it violates those beliefs, your posterior is going to be very different. Now, an outlier, I argue, is an observation inconsistent with a set of points. And these points are presumed generated by a probabilistic process in a vector space. Without that part of it, the probabilistic, we're in other words dealing with random variables here. Without that notion, it's very difficult, I argue, to define what an outlier can be, because that was its original definition, was it lies outside what you expect from some type of statistical or probabilistic probability distribution. Now, outlier detection from that point of view has more than a 200-year history. And the original goal was to reduce bias in models. It was very controversial when it first appeared. It was raised by astronomers when they were taking measurements and didn't believe you should throw out any measurement. In fact, that attitude persisted all the way through for almost a century in standards organizations, where they might weigh an international standard weight and have one observation that was way off, and they would actually compute an average, which would be a biased estimate in this case when it was an outlier. All right. Now, here are the readings I'd recommend if you want to learn more about the history of outliers. I would add one more book to this if you wanted to get into the history of it, and that's Stephen Stigler's History of Statistics, which is still the premier book on statistics over the last several centuries. I've quoted Keats here because I'm pointing out somewhat ironically that I consider an awful lot of the stuff that you read, especially in the computer science literature, on outliers is misleading or wrong. So I'm just saying, read these books first before you read a particular article on a survey of outliers. Now, it's a very complex field, but I've watered it down to two main approaches to outliers. And the first is the distance from the center rule, which should be evident in either of these examples. On the right, we have Tukey's box plot. And Tukey had a particular way of computing outliers using that box plot. Wasn't designed for large samples, so it'll get you in trouble if you try to do box plots on many, many cases. He designed that graph to be computed with a pencil and paper by hand, even though it's now in a lot of visualization programs. It's not very useful if n is very large. Now, the other major approach is the gaps rule. The gaps rule is based on the notion that an outlier is a point that lies very far from its nearest neighbor, which in this case you can see includes the notion of an inlier. It will of course pick up things way in the tails of classic data sampled from a classic probability distribution, but it will also pick up stuff like this. Now, the beauty of the distance from the center rule is that if you compute a set of level curves and you contour based on the assumed distribution of the points, you can get a ellipse or a hyperellipse, for example, for the normal distribution, or multi-normal. In this case, it's a bivariate normal, but even the multi-normal distribution, and then calculate distance to the center of that distribution, and call an outlier something that's that far out in the tails. The gaps rule also generalizes nicely, and it appears in many recent outlier methods, and that's simply points whose nearest neighbor is farther than one might expect from a set of random data. All right, here's the outlier algorithm I devised and published last year in an IEEE journal. It is not unlike those coming out of DB-scan clustering, that team, where you have outliers based on a k-nearest neighbor distribution. These are based on a nearest neighbor distribution. First of all, we can actually work with categorical variables, which normally you wouldn't do. But if you do procedures that used to be called dummy coding and now have various names in computer science, you can do a singular value decomposition on those dummy codes and collapse the set of categories into one continuous variable whose values are derived from the first principal component of that decomposition. Now, one way of dealing with the curse of dimensionality is if P is large, and in practice that probably means more than 50 columns, you can use a random projection to reduce dimensionality. I can't get into that, but it's, I think a number of you know about the theorem on which, or the lemma on which this is based, and they work quite well. No need to do singular value decompositions. This works when all we care about is the distances in the reduced dimensionality space. They work quite well. Then we normalize the columns, which is fairly conventional for multivariate outlier detection. And now if n is large, we go ahead and aggregate. If p is 1, which I didn't point out here, but that's trivial, you just quantize the variable, assign points to whatever bin you've got. I usually work with maybe 100 to 1,000 bins. Assign the points, and that's fine. If p is 2, you can still do gridding for practical problems, and that works quite well. That's been done for many years. The general higher dimensional problem I assign to the variety of Hartigan's leader algorithm. Hartigan is a Bayesian who did a lot of work in cluster analysis and devised this leader algorithm. Once we have that reduced set, which was all those red points in that other diagram we saw, we then compute all the nearest neighbor distances. Since now we're down to under 500 points, that is to say, we pick a radius that is large enough for when n is very, very large, to bring the number of exemplars below 500. And if n is smaller, that radius is going to get smaller, and you'll still have n of somewhere around 500. And now the important thing, the distribution of those distances in that lower dimensional space is roughly exponential. Now, an exponential distribution, we're going to use the upper tail of it. And it turns out a huge number of different probability distributions are modeled quite well with that upper tail, including the normal, the chi-square, gamma, and so on. So we now, by using that exponential distribution, can actually get we can estimate the probability of finding an outlier that far or farther away from its nearest neighbor. And that's what distinguishes this method from the other ad hoc ones, where you throw out outliers based on an arbitrary level. I'll show you some examples. Now, I'll just mention a couple of misapprehensions that people, at least in visualization, have about outliers. My field is statistical visualization, and so when I got interested in hearing some and reading some of the papers in this field by people in visualization, I discovered that they actually think you can find outliers by visualizing, and you can't. For almost every example, there's a good counterexample to show why that won't work. This is one of them, and the problem is you can have a high-dimensional outlier that's not an outlier in a low-dimensional projection, and vice versa. You can have something that's an outlier in a low-dimensional projection, but it's not an outlier in high dimensions. There's some other examples here. That one on the left is a favorite of everybody who does visualization, parallel coordinates. If you haven't seen them before, don't worry about it. My advice is you don't often want to use them, although probably you want to have them in every visualization package that you use. They're easy to plot. What you're doing here, this is 1 point in the higher dimension, in this case 1, 2, 3, 4-dimensional space. So what you do is you plot its value on the vertical axis on age, plot the value on weight, and then just connect the points, and you get a profile. This is about a 100-year-old graph. It's early in the 19th century. Actually, it's more than 100 years. However, what's interesting about this is these two are 2 points that are outliers, significant outliers. And look, if I try to look here, this one's running right through the mass of all those other profiles. You'd never see it. I colored it red to show that. This one is more evidently an outlier. It's not the most extreme on that. So for those 2 points, you're not going to find them. Now, another plot that is a favorite of mine and has many uses, the scatterplot matrix, it's also not a good outlier detector. It has other uses, but I won't go into the details of those red points except to say that the 0.6 is an outlier, but it looks like it's close to the other points in several of the lower dimensions, and yet when you take all the dimensions into account, it is an outlier. Now here is one of the classes, the one I mentioned based on dbScan, which this is taken from a web page with these data, and the author is saying these are all outliers, and they're not. And the obvious reason they're not is there are not enough points to make any judgment of that sort. So these choices of those points was purely arbitrary. Yes, they're farther out from their nearest densities, local densities, but not significantly. So we shouldn't be calling them outliers. Now, other things that involve detecting anomalies have to do with scatter plots, just simple 2D scatter plots. Can we recognize a scatter plot in a collection of many, many scatter plots that is anomalous? In other words, is there such thing as an outlying scatter plot? And here's how we do it. The original idea was due to John Tukey and Paul Tukey at Bell Labs years ago. And with my grad students, I guess about 10, 15 years ago, I made the approach practical by introducing a graph theoretic way of calculating these particular measures instead of things like kernel smooths and other expensive statistical calculations. And the way you do it, the way we did it, was to exploit these three structures. The convex hull on the left, the alpha shape in the middle, which is a convex hull that's the air has been sort of pulled out of it, right? And it's a more accurate representation of the density than the convex hull. A little more expensive to compute, but not too difficult. And finally, the minimum spanning tree. Now, the fact is, you don't need to calculate all of those from scratch. They're all subsets of the Delaunay triangulation, which we use all the time in rendering. In other words, it's one of the methods for triangulating a surface so that we can go ahead and do color rendering and other realistic renderings. Now, what are these scagnostics? Well, there are several that deal with shape. An obvious one is convexity. So on the right-hand side is an alpha shape that clearly all the points are lying inside that alpha shape, and it's considerably smaller than the area surrounded by the convex hull. So actually, that method, although they didn't use the alpha shape, but political scientists have used this particular kind of metric to identify gerrymandering, like what's going on in, I'm not going to name the state, but we know there are a couple of states that have been caught red-handed on measures like this. Also, from where I come from in Chicago, our ward, it's kind of like a little narrow strip that went like this, and, 1 block wide, literally. So, okay, skinny. I'm not going to go into the details of these others because I want to get on to showing some software, but they're skinny shapes, they're stringy shapes, they're collections of points which have high density versus other areas. There's clumpiness, and in a high-dimensional space, in a two-dimensional space, Hartigan defined one measure of clumpiness. He called it the runt test. It involves the longest edge between these collections of points relative to the shortest edges in the two separate collections. So that's a statistic that will pick up on multimodality, or at least bimodality. All right, outlying looks for points whose adjacent edges are extremely long. Density, striated. Let me just show you a picture of the things that look like these 9 measures. One nice thing is, this is a thing called a biplot. It's really just the first 2 principal components. Or, if you want to think of a singular value decomposition equivalently, these are the loadings and these are the scores, all plotted in the same space. So what's nice to see here is these measures, and that took a lot of work, span at least 2 dimensions here. That is, there aren't measures that are almost identical. Now, and this simply shows what certain plots, scatter plots, look like on those measures. Okay. Now, once we've done this, this approach nowadays would be kind of, I guess, called feature engineering. We've made 9 new features out of scatter plots by using these geometric measures. And we can actually treat that as a whole new data set that we analyze. And I haven't got time to run this particular program, But my last grad student took images and processed them as if they were scatter plots. So there are about 30,000, I think it's 60,000 images actually. They were aggregated using the algorithm I described, and then they were subjected to a form of cluster analysis. And what's interesting is, look at these leopard skins and various images, all are now appearing, and he was able to, together, and he was able to show that once you score the images this way, the retrieval is extremely fast for these clusters. Now, how did he call that a scatter plot? He took hue, saturation, and lightness, and on all three of those dimensions, he quantized them, and then filtered the actual image through that to get point sets. So at each of those thresholds, you'd have a particular configuration. He'd do the scagnostics on it, he'd have scores, and then that allowed him to derive a similarity matrix for the actual figures. Now I'm getting into AutoViz, incorporating all the things I've talked about so far, and let's see here. Some years ago, Graham Wells and I developed a program, and it was actually published in Information Visualization, a given journal. AutoViz does this. It's got a very complicated user manual. There it is. Now, just go get a data set and do what it says. Drag, and boom, it does an automatic visualization. Now, what did it do? In this case, it used scagnostics to derive what it thinks are interesting scatter plots. So those are the outlying scatter plots and one or two typical ones, so that you could get a sense of the whole data set. It would take two, you really couldn't plot all the scatter plots. There are too many of them. There are too many variables in the data set. Here, they are plotted as kernel densities and whatever. This is a relationship diagram. It simply lays out the columns, and ones that are highly correlated with each other appear near each other using a graph layout. Now, what's interesting about this program, and led to our thinking about a fairly general solution to analyzing data, what's interesting about it is I can go get a copy of Moby Dick, drag that in, from Gutenberg just online, and bingo, there's whale, here's Ahab, and so on. We just did an n-gram analysis across the entire corpus, and then did a graph layout based on those distances. Well, that's okay. How about a painting by Jackson Pollock? Well, it knows it's a JPEG. This is sort of similar to the third grade joke, and I do like third grade jokes sometimes. A little boy comes to his mother and holding a thermos, and she said, "What is it? What's it?" Well, you put water in this, and if it's cold, it stays cold. And if it's hot, it stays hot. And his mother said, "Yeah." And then he said, "How does it know?" Well, that's sort of similar to this thing. There's a lot of technical detail in here as to how it knows it's a bitmap and the kinds of models that might be appropriate to that. For example, here's some random data. Nothing. It does show you these kernels on the left, but there are no connections in there because they're statistically independent. How about, this one's taken from my book, The Grammar of Graphics. The file itself is an XML file, defining the famous Menard graph of Napoleon's march to Moscow. I think almost all of you have seen it on the cover of Ed Tufte's books. And the XML in there, in the last chapter of the book, I described, I actually digitized his graph with a ruler measuring everything, put them all into a data set, and the XML here describes the actual structure of the graph, the grammar, as I call it, of the graph itself. All right, so, fun thing, by the way, I guess I could take right here out of the, didn't like that. Let's try that again. Well, there we go. There's a whole bunch of JPEGs sitting inside this folder. In other words, you can drag anything in there and it'll know what to do. So that led to the question, what can we do to make a more general visualization system, and that's what I'm going to finish up with, nowadays that can handle big data. And that's what I call AutoViz. I guess you'd say AutoViz 2. So here's the problem. You put all that stuff together, and now we're going to look at a program that, here we are. Now this is a part of our what's called Driverless AI, which is a system that can generate new features and then enter the Kaggle competition. And the program that H2O has done has been able to place in the top 5% of all. We have more Kaggle winners in the company. I think the founder, this is a startup in Mountain View, the founder is obsessed with Kaggle. So we have a number of grandmasters who played a big role in designing the program and generating features and so on. And the program does very well in those problems. And needless to say, it does very well in predicting practical problems for the insurance industry or credit risk and other things that people do in prediction. Now, this is the AutoViz section of it. So in other words, and by the way, I'm analyzing here a tiny data set called Iris. And some of you know it. It's ancient. It's Sir Ronald Fisher's collection of measurements by a biologist named Anderson. And they're measures of iris flowers. So I'm going to run AutoViz, visualize, and the program prepares a visualization, and this is what it finds. It finds one scatter plot out of all the possible ones that's highly correlated. It locates a number of skewed histograms. 2. It also computes a method Tukey developed called gapping, which is an extreme form of a test for bimodality. It looks for distributions that have significant gaps in the middle of them. There's a biplot, by the way, and as some of you know, there are 3 species of iris flowers, so this is one of them here, and these are the other 2. So at least that much of the structure is coming through. Here's the correlation graph, which is very similar to the one that was in the old AutoViz. The only change here is that I used non-parametric measures from a statistical point of view so that you could correlate 2 categorical variables through the use of something called phi squared, a categorical and continuous variable, or 2 continuous variables. So all the variables in the data set end up in this diagram. And if 2 things are highly correlated, they're going to be near each other. Then you see the parallel coordinate plot. What's done inside here, as you can see in the legend over there a k-means cluster analysis. Also, it estimates the number of clusters in the data set. So as you know, when you run k-means, most of the time you have to run it with 2 clusters, 3 clusters, 4, and there are various methods for deciding when you should stop. This does all that automatically, and what I like about it is, just to verify performance, there are 3 species, and it found them by and large. All right, let's add another data set. This one, I think, is from Kaggle. It's BNP. So it's uploading the file. Now you notice it's computing selected statistics. So it's going through there and pre-computing statistics that it thinks it's going to need. This file is fairly small. It's 114,000 rows and 133 columns. So we'll visualize that. And now it's doing the aggregation, analyzing the data set, and the visualization's ready. And you see some of the usefulness here. For example, we've located one histogram that is extremely negatively skewed. Spiky histograms are histograms where the tallest tower is a multiple of the short ones. And here are skewed histograms using a particular robust measure of skewness. And here's the outlier. Now here's the univariate outlier computations. And works very nicely. Doesn't false alarm. Although, let's check something out here. I'll go back and add another data set which has 1 million observations, and they're all normally distributed. So it just read it in, using, by the way, a very fast import procedure called data table, which was developed at H2O. It's in the R package as well. It's one of the R. Yeah, I just wanted to point out, these are normal random variables. So there shouldn't, in the sample, have been outliers, but there is here, and that's because the this value is way out here with a 5. The alpha level selected for that particular statistical test is 0.01. So 1 time out of 100, you're going to see an outlier. We could tighten that up if we decide that's still not sufficient, because that's going to give us more false positives than we wanted. All right, I'm going to stop there for questions. I can show you a bunch of other data sets. The essential thing about this program is I'm running it on just a MacBook in Docker. The MacBook doesn't have GPUs, but our industrial strength version is running in certain places on giant GPU systems, NVIDIA GPUs, with some people using Amazon, AWS, and so on. If you do that, this visualization system will be able to do visualizations on 100 million rows. And that's pretty useful. So, any questions?
Let's go this.
Put you away, I guess. Too many details.
I'm a computer scientist, not a statistician, but I happened to learn in the 80s this strange thing that nobody uses.
That strange thing?
Spearman correlations in the rankings.
Yes.
So some things you talk categorical, you talk intervals.
Right.
Rankings seem to be neglected. How about?
Actually, I based that correlation plot, large correlations on Spearman originally. The reason I switched back to Pearson was that I started to think, yeah, Spearman would pick up curves like this, or it'll even be 1 if all the points lined up on an L shape.
Yeah.
But I was trying to figure, would people be as interested in that? Here's the thing, Pearson,
It can mislead people, I understand.
if you have a perfect correlation, that tells you, don't let those 2 variables into the same regression model or GLM or other models. So I waver on this. Yeah, good point.
Safe.
Yeah. There are so many statistics that can be useful in visualization, and the people in visualization, in my experience, at least at VisWeek, have no training in statistics. So unfortunately, we haven't seen a lot of applications that use some of these things like Yule's Q, measures like that. Nobody's using them in visualization. Yeah. Any others? Well, thanks.